Welcome to session number 8 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam. In this session, I'm going to talk about design of various passives on different laminates or substrates, right? So there are three of them which are very common. First of them is the PCB or printed circuit board. Now this laminate material usually is a fire resistant grade 4 material or called FR4. Its dielectric constant is 4.6, but it can vary from 4.1 to 4.6 depending on the choice of a particular material, right? But all of them are FR4. Their loss tangent is 0.02 to 0.03. Now this is a very inexpensive material and is widely used for designs up to X band. But if you want to use a low loss tangent material, then lots of materials are available in standard thicknesses from Rogers, so you can make a choice for that. Now the issue with PCB design is if you want to do a multi-layer PCB, then you are restricted on the vias, right? So what are the vias? Vias are basically contact between two metal layers. So what the stack is, okay, a PCB stack is nothing but a sandwich of a dielectric material with the metal in between, right? So this can be stacked up to multiple layers, right? Now the issue is you can do what you call a vias, which can be filled vias. So here is example of a filled via, right? So this via is totally filled. So first what they do is they drill through, right? And they'll drill through and then they fill it with some kind of a material, right? Conductive material. So that will be called a filled via. Now over here you see the other one is a plated through via. So what it means is that they drill through, but then they only plate the walls, right? Now it is easy to do this between two layers. Now the way the multi-layer PCB is done is they do this two-layer PCBs, right? And then they can do these vias, right? But then they stick them together back to back using something called core. So if you see here, there is something called core, right? So that thing is called core. Now the issue is, can you run vias through the core? Well, the answer is no. Can you do metal structures which can stick together? Yeah, but how do you connect them, right? So you are allowed to do a plated through, right? A plated through all the way from the bottom metal to the top metal. But then doing the buried vias, you have a restriction that you can do in the individual two-layer boards and then stick them together. Then what do you do when you stick them together? Can you do vias in the core? Answer is no. So this is a big restriction in a uh, PCB design. So if you want to do a circuit, right, you can do all the way through via, because once they stack it up and they can then drill through all the way from bottom to top, and then they can plate through. So that is allowed. But the problem is when you stick them together with the epoxy back to back, then can you do a buried in the core? The answer is no. So this is a major restriction of most of the PCB manufacturers. Now I may be wrong, maybe the technology is advanced and I don't know, but this is what I know of. Another thing is that these vias usually are going to be like, these days you can do almost 4 mil or 3 mil vias. So basically the drill size is at least 8 to 10 mil, and when you plate through, you are left with a via which is going to be a 3 mil via. So a plate through via would be a 3 mil via. A filled via can be a 3 or 4 mil via, but the drill size there, there is a restriction. So there is a separate restriction on a filled via. What is the smallest dia you can do, and a plated through via, the dia you can do, right? So this is an important specification. Next is the via from the edge of the metal, right? So via from the edge of the metal, there is a restriction. It depends on the drill bit they're going to use, right? So these restrictions are there, right? Now this PCB is the shortest turnaround time, and you can do this, and it is available. There are many manufacturers available in different countries, right? But then they have some limitations. Again, the trace widths or the metal widths can be close to 3 or 3.5 mil, and the gap can be also 3 to 3.5 mil. So as a designer, when you lay out a PCB, you have to be cautious what a manufacturer would do, right? Whether he can do it or they cannot do it. Okay, so this becomes very important in case when you are doing antennas and filters and stuff like that, right? So you have to be careful on that. The next thing which I'm going to talk about, okay, is this, right? So let me see if I'm recording. Yes, I'm recording. So let's go full screen. Okay, so there is something called low temperature co-fired ceramic, and there is a high temperature ceramic also, right? So HTC or LTCC, right? Most of the multi-layer capacitors, or most of the multi-layer inductors also, okay, in a printed technology, done in HTC. But then there is a process available which is called LTCC, or low temperature co-fired ceramic. Now the curing is done at around 800 to 1000 degrees Celsius, right? And it's over a period of cycle where you have to maintain a certain temperature profile along the time. Now, what is the LTCC process? There are tapes. Okay, these are like the what they call the green tapes. Okay, these tapes. So I'll just show you. Okay, so the top figure you can see. Okay, the top figure you can see over here that there is some form of a tape, right? This tape is a flexible material, easy to cut. Okay, this is a calcium borate, right, with some kind of hydrous form, so that you can easily cut through or punch through holes or cavities, right? So these are provided in the form of reels of tapes, which are called green tapes, right? And they are available in standard thicknesses, right? So what you do is you get this reel of tape and then you cut it into square blocks. So the figure number 3, basically figure number 3 is showing you that it has been cut into square blocks. So this is called blanking. Okay, so the tape comes with polyester on both sides. So once you have a polyester backing, what you do is you can cut it into square blocks of a standard size, and that has to fit a frame, and that's a metal frame. Okay, the metal frame is going to have poles, right? And these poles can be along the length of the metal frame, or can be just the corners. Okay, so what you do is you punch holes into this green tape, and so that you can stack in that frame one over the other. So this cutting this into standard square sizes or panel sizes is known as blanking. You usually do not remove the polyester backing, right? While you are punching holes, whether it's for any vias or registration holes, you do not remove the polyester blacking till you go to the point of lamination, right? So I'll tell you what that is. Okay, once your blanking is done, okay, you can do what is called screen printing, and then you are going to use metallic ink, or what you call a special material, okay, which can be a silver based or a gold based. Sorry. And you can basically lay out your circuit on those tapes, right? And then what you can do is, if you have one via, you can punch via mechanically or through laser, right? And then there are dimensions, like you can go vias from 25 microns to something like 50 microns, or maybe 100 microns, right? And then you can fill it up with another conductive material, right, which may be silver or gold based, right? And that's how you are going to create the vias. So you create this 2-layer uh, tapes, which are printed with circuit on either side, right? And then you also fill the vias. Once you start stacking them one on the top of the other in a frame, in a metal frame, like for example you see here, there is a frame in last figure, right? So in the last figure, you can see here the fourth figure from the top. You can see that there is a stack in a frame. right? So basically you can once you put them on the frame, you can fill in the via, and then you do the screen printing, and then basically you can stack up the other one, right? So you can ply on one on top of the other the layers, and then you can pressurize them so that they stick together, and then you can put it in an oven, right, and cure it. So that is called co-firing, right? So it is very simple to do that, right? Only thing is what happens with uh, this kind of a calcium borosilicate is once it starts crystallizing, right, then or losing dehydrating or losing water, then it shrinks. So if it shrinks evenly across all layers, then it's going to remain flat. But if, for example, the shrinking is not uniform across the layers, then it may buckle up. Okay, and there are things to stop buckling up. Okay, one is that you do a even loading of metal on different layers. Even loading, I mean, is that the same density of metal loading is there, right? And this will cause the shrinkage to be more uniform. That's one thing. Second thing is when you are curing it, you can flip the entire metal frame while curing it, so that the entire layers are heated equally, right? So that can avoid you know the buckling up. Another thing is that if there are large metal chunks, you can cut out what you call slots for stress relief. Okay, this is even done in gallium arsenide process. If you have large metals, thick metals, you usually cut slots in them to avoid stresses, right? So this is another process, okay, where you can do multi layers, anywhere from 8 to 32 or 40 layers even, and it all depends on the user. Now the top and the bottom, so let's see here. Okay, the top and the bottom can be post firing, they can be processed. And why you need that? You can create pads which are copper, you can create pins which are copper, you can also do what is called frames or heat sinks right on top of the top layer, right? And you can also do uh, top layer, you can also do some thick film resistors also, right? So that is what happens with post processing. Now you already know that what is a blind via and what is a buried via. You can also do a stacked buried via here. You can do buried integrated capacitor. You can do staggered via, like vias can be staggered, right? And they are very stable. Then you can do thick film resistors which are buried, right? And you can also do cavities. Now in case of cavities, after you plate it through, you can insert a support for the cavity using some form of a sacrificial material, which after post processing you are going to remove, so that you have a clean cavity without buckling and all that. Now calcium borosilicate is not a good thermal conductor, so all the heat has to come out through these vias only, right? And heat has to go to the ground. Now in this case, the thermal conductivity of these vias is good, right? But then it is not going to be uniform, in the sense that you are not going to have stacked vias from top to bottom. So in that case you can have thermal vias which will take the heat from different layers and conduct it to the ground, right? So that is a stack up looks like in case of a LTCC. Now let's look at the material. Okay, the green tape comes in two standard thicknesses. One is 10 mil, other is uh, 5 mil. Now I'm talking about Ferro LTCC process, and metal system is A6S, and this process can go up to 100 gigahertz. Now there is another manufacturer which is DuPont, right? And they also have something similar, which can be a silver based or a metal based material system, or it can be a mixed gold and silver material system. They also have tapes which usually do not shrink, right? So then shrinkage is not an issue. But this particular uh, stack which I'm going to use from Ferro, right? This is going to have a shrinkage of 15.3% on X and Y. So all the EM simulation you have done on a post-fired dimensions, that is the shrunk dimensions. But when you go to manufacture it, you have to increase the size of every dimension by on X and Y by 15.3%, right? And same thing is about the height, right? So if you have a 10 mil green tape, so that is going to be 254 micron pre-firing. Post-firing it will be 193 micron, right? Similarly 5 mil, which is 127 micron, post-firing will be 97 micron. So you can use either of them, right? There are some non-standard thicknesses like 60 micron or 100 micron, but then they are going to be costlier, right? Now, another thing is, let's look at the two important factors here. One is the dielectric constant. The dielectric constant is 5.9 or 5.8, right? And from the graph you can see that it is very flat across 1 gigahertz to 100 gigahertz. And same thing is with the loss tangent. The loss tangent is close to 0.002, and it is all flat across the frequency. So this is a Ferro green tape. Next is this can be a silver based system or a gold based system or a mixed metal system, right? Now pre-firing, usually this metal thickness is large, but then post firing it can come anywhere from 6 to 9 microns, right? So in your EM simulation the metal thicknesses will be 9 micrometer. Okay. Now here what I'm showing is post co-firing processing, where you have added these shields, right? These are metal frames, right? There can also be what is called heat sinks. You can attach heat sinks to this. You can mount surface mount components. You can even bond the chip or a die. You can bond it, right? And then you can put a lid on it and take the air out and hermetically seal it, right? So this can be done. Now the materials is chosen or is designed such a way that the metal contraction or thermal expansion is the same as the tape, temperature coefficient of expansion. Okay, next thing is, so that when you do it the shrinkage is uniform. And second, so shrinkage is one thing, and then coefficient of expansion is another thing. So across temperature cycles, if you see, then this TCE is going to be very less, right, on this material. And shrinkage is uniform for metal as well as green tape, right? And next thing is the thermal conductivity of the vias and thermal vias. So thermal vias, they have 50 watt per millikelvin, right? So here there are some electrical properties which are of interest to a designer. That dielectric constant is 5.9, loss tangent is 0.002, insertion loss, right, at 10 gigahertz for a trace, right, which is an inch is 1.8 dB. Now the width is not specified here, so that's unknown here. Bulk resistivity is 10 raised to 12 ohm per centimeter. So basically it's a insulator. That's what it's saying. Now this is the material system for the metallization, right? This is an all silver based material system, and there are numbers specified here, right? So for inner conductor I'm going to use CN33398, right? And for the surface conductor I'm going to use 33391, right? And see, for different purposes, like for example via I'm going to use 33343. Okay, so these are the various materials which are provided by Ferro, and you can use them. For resistor, thick film resistor, there is FX87, and it is 100 ohm per square kind of resistivity, right? Pre-firing, the thicknesses of metals is 9 to 12 micron. Post-firing it's 6 to 9 microns, right? Resistivity is 1 milliohm per square. Okay. Now one more thing is there. You do not have to what you call precondition the tape. Okay, so this system you can directly punch in and screen print and then ply. You do not need to precondition the tape. to a certain temperature. Next is, in case the shelf life is sufficient, that's fine, but in case you exceed a certain shelf life, there is a thinner which is provided, okay, which is Ferroflow thinner 0804. Now you can use that, but my recommendation is that you use a fresh off the shelf fresh materials rather than using thinning, because it leads to a lot of problems in the final product. So that is the all silver based metal system. Okay, so now I am going to use this stack up. So let me tell you what this stack up in ADS will look like. It will look like M0 to M7, which I am going to create. Each of them is going to be 9 micron thick, and it is going to be silver, so it is going to be 6.17 e raised to 7 Siemens per meter as conductivity, which is over on the left hand side. Then for the top, if I do pads and all that, I'm going to use copper, which is going to be 5.8 E7, right? And the thickness is again 9 to 10 micron, right? Then for the thick film, I'm going to use FX87101. So in my stack up, I'm going to declare this as 100 ohm per square, right? And then for soldering, right, the top pads, I can also plate them with the solder material, which is going to be 0.71 E7 conductivity, right? So this is what is going to be there. I also have a layer which is going to be a dielectric via or a cavity. Now momentum will not allow you to do this simulation with the cavity, right? So stack can be there with a cavity, but momentum will not allow you a cavity for simulation. So you have to use EMPro or something like that. Now the material is borosilicate, which has epsilon r of 5.92 and loss tangent of 0.002. So this I am going to create in ADS before I proceed to do any of the designs. So if the stack is going to look like this, right? So the thermal conductivity of silver filled via is 174 watt per millikelvin, while that of thermal vias is 50 watt per millikelvin. Now if you see, the conductivity of the silver filled vias is more than that of thermal vias, right? So one may question, why don't you just use silver filled vias with a higher conductivity, thermal conductivity? The question is, you cannot stack them up all the way through, right? So in that case, you have to use a via which is going to be a thermal via, right, which is going to be 50 watt per millikelvin. We are not going to do any thermal simulations on this, right? So I am not going to draw these vias, right, or a special material for this via. I am going to use same silver material for the vias. Okay, so this stack I'm going to create in ADS. Now I'm going to pause while I do that, right? Okay, now I have created a 7 metal stack using the LTCC 97 micron thickness is green tape, and then I have one more additional metal which is for thick film resistor, 100 ohm per square. Now you save the stack and close it. Okay, so what we are going to do now is we are going to make a new folder, and we call this as let's say lines. And here I'm going to create a 50 ohm line. So I'm going to create a schematic, micro MICROSTRP, right, uh, microstrip line, and create a schematic. And here in this schematic, I'm going to create a 50 ohm microstrip line on LTCC process. The signal is on metal 7 while the ground is on metal 6, right? So I'm going to go to tool LineCalc, open LineCalc, and in this case I'm going to enter the substrate details. Okay, so the substrate epsilon r is 5.92, height is going to be 97 micron. So height is going to be 97 micron. Thickness is going to be 9 micrometer. So 9 micron. Conductivity of silver is 6.17 E7. 10 delta is 0.002. loss tangent, and that's it. That's for the substrate, right? Then we make sure that this is going to be 10 gigahertz line. So I'm going to make a 50 ohm line. So I put here 50 ohm, and then the length of the line is 90 degrees or quarter wave. I want the units to be micron. So then I hit synthesize. And 139 micrometer is roughly the width, and the length is roughly 3900 something, right? So I'm going to go and make a layout for this, right? So this is the information. Now let's go ahead and make a layout. Okay. Okay, previously we have done this 50 ohm line, and we found out that the FEM results from ADS were differing from the MOM results, momentum results, right, in ADS. And this time we are going to validate it against FEM in EMPro. So let's create a new layout for the same schematic. Let's adjust the grid size. So I want to keep the grid to be 0.1 micron, and minor grid as 1, and major grid I leave as 5, and I'm going to save this for as a layout preference for the next simulation, for the next layouts. So now here we have, I'm going to use metal 7 to draw a line. Now yeah, so I'm going to I'm going to draw a line which is 139 in width. So first of all, I'm going to set the all the snap grid options. Okay, so I'm going to enter the coordinate entry, absolute value as 0, 0, where I'm going to start drawing the geometry from. And okay, so I have to change the metal from conductor to metal 7, and I will redo this again. So metal 7, yeah, there you go, metal 7, and then I'm going to draw a rectangle and insert coordinate entry. Insert coordinate entry, uh, 0, 0 as absolute entry, and then say apply, and then the dimensions. So y dimension is 139, and the x dimensions are 300 something, right? 300, yeah. Okay, so this is the line, okay, quarter wave line as per the LineCalc. So I'm going to go ahead and put the ground. So I'm going to put quarter wave on both sides of the microstrip line. So the way to do it is just take this structure, rotate it out. So rotate it out, and I am going to just extend it to the edge, right? So delete this one, extend this to the edge, right? And then I'm going to repeat this structure at the top. So I'm just going to do copy this structure. Yeah, I'm sorry, not move, copy the structure, right? So I'm going to copy the structure. Then I'm going to extend the structure to be a single structure and delete this is square, right? So now I have the layout of a microstrip line which is 50 ohm. I'm going to put port 1, then I'm going to put port 2, and port 3 is a ground reference to 1, and port 4. So snap to grid to edge, right? So snap to edge is enabled. So there's port 4, and I'm going to move this port, ground port, under the signal port, remove this additional piece of line, and then I'm going to move port number 4 underneath port number 2 and move this additional piece of line. So now I have the structure ready. Now I'm going to go and create EM's simulation setup, and I'll go to substrate, make sure the substrate which I have defined is over here, right? Then I am going to go ahead and do port editor, and I'm going to add uh, so yeah, 3 to port 1 and 4 to port 2, and I'm ready for the simulation. So before that, I should see a 3D EM preview also. So what I'm going to do is first mesh, edge mesh, transmission line mesh, and then I want to also save the output, all for all the frequencies. I want to save that, and then I'm going to set the uh, model to be saved, right? Show that the model is saved, and I'm all set. Everything is right. Adaptive frequency, I'm going to simulate from 9 gigahertz to 11 gigahertz adaptive, and I'm going to create one more point, which is going to be uh, what you call DC point, right? So I'm going to create a DC point here, add single. So adaptive, instead of that I'll use single and 0 gigahertz. So I'm all set for hitting simulate button. So let me just check, you know, all frequencies are saved. And one more thing, yeah, I'm going to change the data set to show that this is a method of moment simulation. So I'm going to rename this to an extension of MOM, right? So this is a momentum simulation, okay. And then I'm going to hit simulate button. So I'll go back to EM setup, and everything is all set. I can hit simulate. So meanwhile this is going on, I will put you to pause. It is computing green functions for the substrate, so it is going to take some time. So I'm going to put you on a pause. One more thing you should see is 3D EM preview to make sure that their ports are connected properly. So basically they should go from the ground to the signal, right? So that's correct. Okay, so now this green functions computation is going to take some time. I'm going to put you on a pause, and when it comes finishes, I will come back. Okay, the computation green functions is done, substrate computation. Now it is going to mesh it. Okay, so this has done the simulation, and the impedance looks like 50 ohm from DC to 9 to 11 gigahertz. So let's go ahead, and so this looks right. So let's go ahead and do FEM simulation. So I'll go ahead and go and change. Okay, so I'm gonna go and change this simulation to be, so everything is okay. Okay, so I'm going to change the file. Instead of MOM, I'm calling it FEM now, right? I add FEM to the name of the file, and I'm going to go to simulation setup and simulate again. So I'm just making sure that I'm going to write to a right file. Okay, so I'm going to go ahead and go change the simulation to FEM, and then hit simulate. Okay, one more thing is that I am going to go to the mesh options. So go to options, mesh. Okay, so all frequency you have to save. Options, mesh, and then go to advanced. And advanced, use the finest mesh after the convergence, and then hit simulate. It is going to replace the original simulation file. Say okay. So the EM model file, right? Say okay, yes, and let it simulate. Okay, so what this is, it's doing adaptive mesh, and it is increasing the number of cells. so as to reduce this error function delta S below 0.02. So let's say in next iteration, oh, it has gone up. Okay, so it is going to go down to less than 0.02. Okay, now it has, right? So now it has found the finest mesh for a given error, and now it will simulate all the frequencies. Okay, so now what we see here is that FEM in ADS is giving much different results, right? You said 9 to 11 gigahertz, so DC is over here, 9 to 11 gigahertz is over there. So basically this is much different from what momentum gives you, right? So we have to make a conclusion here. What are we going to rely on? So let me put a marker here which just says that this is FEM results 9 to 11 gigahertz, correct? Now what I'm going to do is I'm going to create the same structure in EMPro, and okay, so now what we are looking at is that FEM results for the same structure in ADS is much different. So this is not acceptable. So we have to figure out which one is to be relied on, whether MOM or FEM in ADS. Okay, so the one way to validate it is to create the same structure in EMPro and do FEM simulations over there. So that's what I'm going to do. Let me put here some text. Let's see. Right, so this is a lot of variation. This is unacceptable. Okay, so I am going to, so I'm not happy with this because momentum is over there and FEM simulation is over here. Right, so I'm going to put you on a pause and create a structure in EMPro and simulate. Okay, so here is the result from EMPro on the left hand side, and I see that the result from EMPro is same as that in momentum, but FEM simulation in ADS is much different from FEM simulation results in EMPro. So let me just label it here. Now there is a question to ask, Keysight guys, that if ADS is using same engine for FEM, why is, first of all, why is method of moment results so different from FEM? And second, FEM in EMPro is giving same results as MOM in ADS, while the FEM in ADS is not matching the FEM in EMPro. So Keysight guys have to make a note of this, and they would have to answer that. What is going on? Maybe it is the extent of the port, right? Maybe it is the extent of the port. So let's see, in ADS, is there a way to set the extent of the port? I don't think so, right? So there is no way to set the extent of the port other than you just set the ground reference. So there is no way to do that. Okay, let's see. So I don't see that. If somebody can advise me how to change the extent of the port, or if that is itself the reason for why the results are so different. I don't think so. I don't think that that's the reason why the results are so different. Okay, so I'm going to just label this, and I'm going to rely on EMPro for FEM simulations, not FEM in ADS, because it is way off. Let me label this right. So I will put a label here, FEM in momentum. No, not momentum, FEM in ADS, right? So FEM in ADS, right? ADS and MOM in ADS. So the next thing is MOM in ADS. Why is FEM in ADS so different from MOM in ADS? Right. While the FEM in EMPro is same as the MOM in ADS, so these results don't match. Right. This is close to 52 ohm. Okay. So I have made my conclusion. I am going to use MOM in ADS for my all designs. And when I need 3D simulations, I'm going to rely on FEM in EMPro because they seem to be more accurate, right? Okay, so I'm going to set it up for the next simulations. I'm going to do a Wilkinson divider, right? So I need a 70.7 ohm line instead of a 50 ohm line, right? Okay, so let me just close this and let me just get set up. I don't see that I've done anything wrong in ADS. There is no way to change the extent of the port in ADS. Okay, so I'm gonna stop here. There's nowhere it is given. Okay. Okay. So I'm not going to rely on FEM in ADS. It's way off. Though it seems to use the same engine as FEM and EMPro. I don't see any other difference. And there is no way to change the extent of the port in ADS. Okay. Okay. So mom looks more accurate in ADS. Same as that in FEM. Okay. Okay, so let me set up a 70 ohm line. So I'm going to make a new schematic and I'm going to call it micro strip strip no strp 70 strp 70 microstrip 70 ohm, right? 70.7 or 70 underscore 7, yeah, underscore 7, and say new schematic. Now I'm going to go to LineCalc. And here in LineCalc, I'm going to change, so I'm going to put back 5.92 as epsilon r, height as 97 micron, thickness as 9 micrometer, conductivity as 6.17 E7, okay, and 10 delta is 0.002. And I'm going to make a 70.7 ohm line and 90-degree long. And I want results in micrometer. And I'm going to hit synthesize. So this is 65.5 as the width and 3,832 point something as the length for a quarter wave long line at 10 gigahertz. Okay, so I'm going to make a new layout quickly. I'm going to make a new layout for this one. and I am going to start with a corner at 0, 0, and yeah, coordinate entry absolute 0, 0, say OK, and then oh sorry, this is conductor, so let me change to metal 7, and then draw a rectangle with origin at 0, 0 absolute, and then relative, and the height is 65.5, and the width is 382, 3832, 3832. Let me just check it. Yeah, so it is 3832 micron. Say okay. So there's my microstrip line. Now I'm going to put a quarter wave ground on either side. So I'm going to take the length and make it the width on metal 6, and then I'm going to rotate it and then stretch it to along the length. So basically I have a quarter wave on either side of the line. This is the best thing which I have seen in case of impedance control, is to put quarter wave ground on either side. Okay, so I'm going to remove the extra polygon here on the ground plane, which is the top one, right? Not the bottom one, the top one. Yeah, so top one, delete. Okay, so now I have the structure for a 70 ohm microstrip line. I'm going to put the ports. Okay, port 1. No, not here. Port 2 is the signal. So first you do all the signal ports, and then you do the ground reference ports, because in simulation this is going to remove the ground reference ports. So this is port 2, port 3 is a ground reference for port 1, and port 4 is a ground reference for port 2, and then I'm going to move them underneath like this, remove this line, and I'm going to move port 3 under port 1 and remove the additional piece of line, and I'm all set. Now I'm going to go to EM simulation, create, go to port editor, right, and port 3 is a ground reference to port 1. Okay, let me extend this. Port 3 is a ground reference to, oh no, oh, so let me see if I can correct that, because no, I cannot move it. So what is the way to correct it? Maybe I can just delete the ground. It doesn't move, right? Oh, now port 3 is gone, right? No, this is not going to work. Oh, the problem is I might have to remove it and place the ports again, because it doesn't let you correct it once you do a mistake. Port 3 is gone. I can't add port 3 now. Okay, so what I'm going to do is I have to delete all the ports now and put them back again. Okay, so I'm going to delete all the ports, right, and I'm going to put the ports back again. Port number 1, port number 2, port number 3, directly I'll put it, port number 4, and I'll change the metal layer. So this is 1, sorry, this is 2, and this one is 2, and this one is 4. Okay, so I'll change the metal to metal 6, and then I'm going to change port 3 to metal 6 also. So port 3 to metal 6. Okay, so I'm all set. Yeah, so make sure that they are on the right layer. So I'm going to go back to EM setup, and this time I'm going to not do mistake. Go to port editor and extend this down, so clearly 3 is reference to 1 and 4 is reference to 2. So I'm all set on the ports. Okay, one more thing is a port reference was 50. Now I'm going to make it 70. Okay, so leave it on auto, because when you do DC simulation, the DC point is going to just get stuck if you don't leave it on auto. Okay, maybe the port has to be 70.7, right? Not 70. So let's go back and put that 70.7. And this is also 70.7. So 70.7 is going to be the normalizing impedance, because these are, generalized as parameters, right? So that will be the center of the Smith chart. Frequency is from 9 to 11. And I leave it to adaptive. I will not add DC point. Then under options, go to mesh, edge mesh, transmission line mesh enable. Then ensure that the model is created, and under, I think we are all set. Okay, save for all the currents, frequencies, save currents for all the frequencies, and then you are ready to hit simulate button. So once this simulation is over, we are going to see S11 and S22 at the center, and the center this time is not 50, it is 70.7, correct? So this is going to be 70.7. So it is reducing the mesh right now. It's meshing at 11 gigahertz. So there is a mesh reduction in momentum. Okay, so here you go. It has meshed at 11 gigahertz. Now it is simulating. Okay, so now I'm going to plot this on Smith chart. S11 and S22. S11 and make sure I'm recording. S22. Okay, so they are off center slightly. Okay, so let's now put a marker and see what they are. So this is normalized to 70.7, isn't it? So I will go here and set this to 50. No, 70.7, because the center is the 70.7. So let's put here 70.7. So now it will read, it has read 76. It has to be 70. So we are 6 ohms in error. Now is this an error because I feel that this is a thick metal and mom does a computation on thick metals? So let me not change this. Okay, I am going to go and create the same structure in EMPro and see what is the impedance. Yes, I can shrink the width of the line, but I'm not going to do that because I'm not sure whether the momentum gives the right resistance, because it's using thick metals, right? So I'm going to go and change it. So here I have created the EM simulation. 70 ohm is the center. Now this looks much better than MOM. So this shows that 9 to 11 is at 70.7 and the DC is a little way off. So I am going to not change the dimensions of the 70 ohm line. I'm going to use the same because I don't believe in momentum as much as in FEM and EMPro, right? So I'm going to just use the same width of 65.5 micron for a 70.7 ohm line, right? Okay, so let me just close this and let's start creating a Wilkinson divider. So first of all, I want to create a Wilkinson divider using this 70.7 ohm line, which is 65.5 micron width and 3832 micron in length, right? Okay, so let's go ahead. Let me get started. Let you put you on pause. Okay, so here I'm going to create a new schematic. Call it Wilkinson divider two-way, right? So go to files, create a new folder and call it passives LTCC. Yeah, passives. Okay, dividers. Okay, so let's call this folder divider, create a new schematic. Wilkinson div two-way. Okay, so it's a two-way Wilkinson divider. Okay, the divider uses 100 ohm resistance between the two branches. So I'm going to use a thick metal film resistor, 100 micrometer square. Right, so first of all, let me find out trace, and truncate is the end, and the width is 65.5. So I'm going to start at the origin at 0, 0. Insert coordinate entry, absolute 0, 0. Okay, so now I need to go certain length at an angle, right, on metal 7, right? Okay, on metal 7, I'm going to create a trace at the origin at 0, 0. And I will take these two lines so much apart that you can fit in two connectors at the edge, right? So I'm going to go to 382, 3. So I'm going to go at a 45-degree angle, right? So it allows me to do a line at 45-degree angle, isn't it? Okay. So let me get the length of the line. The length of the line is 3,832, right? 3,832. So that will be the trace length. So I am willing to put 380 or 400 going away from the center, probably at an angle of 300, at an angle of 45 degrees, isn't it? Don't want to grow like a square, right? Okay, I'll go at an angle of 45 degrees. Okay, there it is, 45-degree angle. Okay, on this I want to go 386, and then I want to go the remaining. So 3,832 minus 386. Okay, let's use a calculator. Okay, 3,000. I have to go 3,832 minus 386. Okay, let's use a calculator. 3,832 minus 385. Okay, 3447. 3447. It's over here, long way to go. Yeah, so that's almost it. And I'm going to double click here. Double click that. Okay, there I am. You want to maintain a straight line. Okay, double click that. Double click. Okay, done. So let me just click tick and check the length. It is 3,991. So 3,992 minus 3,832, right? So I'm in error right now. 3,992 minus 3,832 is 180, 160. So I have 160 longer lines. So I'm going to shrink this. Move, edit, move relative 160. Okay. So, oh, sorry, wrong way. Let's do an undo. Minus 160. Say okay. Okay, once I'm done with this, I'm going to take this structure, copy it and flip it. Copy it and then flip it along x-axis and then match these two corners. So I'm going to move this corner to that corner, and that's my Wilkinson divider. Now I need to add a 100 ohm resistor here, so 100 ohm per square. So I'm going to use THFR, thin film resistor. I'm going to use 300 and something by or 250 by 250 or 300 by 300. As long as it's a square, it is going to be 100 ohm, right? So that's it. So that I'm going to place at the center. So let me just center it out. Okay, still let me just center this out. Okay, so I'm going to move this down to the center. So let me check how much I have to move from this edge. Okay, this thing divided by 2. Okay, so I'm going to move this, move relative, and 150 something, 155, that's almost the center. Then I'm going to use metal 7 to connect this. Metal 7. So I'm going to put the same width of the line to connect to the resistor. Okay, 65.5, right? So let me just put here metal 7, 65.5. Okay, I'm going to rotate this and I'm going to center this. Okay, center this to the resistor, shrink it to the size, and copy this and do it on the other side too. Sorry, copy this to the other side, isn't it? Okay, so this is done, but then this contact I need more overlap, right? So I'm going to copy this structure and repeat it again here. So I'm going to copy this, rotate this, and then put it on either side of the resistor like this, and make it the same size, and do the same thing over at the bottom. Okay, I'm done. Now I want to take the two lines to the edge, right? So I need to attach 50 ohm line going to the edge, isn't it? So my line is 139 micron wide. So I'm going to put here some line which is going to be some length, let's say 160, 150 long and 139 wide, right? And say okay. And I'm going to center this line. Okay. So no, that's not going to center this. Okay, let me okay, let's center this. Okay, and I'm going to extend this to the right beyond the resistor and copy the same stuff on the other side. And I'm going to copy the same 50 ohm line to the input side. Okay, little more to the right. Okay, done. Now I'm going to merge all metal 7 layer as one. So I'm just going to remove the measurement stuff, which is at the bottom also, right? Now bottom, yeah, remove that and select all metal 7. This, and this one, 50 ohm, this connection, everything, and say edit, merge, union, and say okay. So now everything has become a single this thing, single metal. Now I'm going to put in, okay, the ground plane, quarter wave. So roughly 3832, right? And there you are, 3800 and something. Extend it to the edge and make a copy of this and just repeat it on the top and then extend it all the way down and remove one of the polygons. Okay, so we are set with the structure of a Wilkinson two-way divider with a 100 ohm resistor. Now I'm going to put the ports. Okay, so let's put the ports. Okay, so port 1, port 2, port 3, port 4 is ground reference to 1, port 5 is ground reference to 2, port 6 is ground reference to 3. Now I'm going to move them underneath quickly and remove this additional line. Same I'll do for port 2. Remove the additional line, delete, and here this one I'm going to move to port initial line. So we are all set with the 3 ports. Now before I simulate, I should see if everything is okay. So I'll go to port editor. 4 is the reference to 1, 5 is the reference to 2, and 6 is the reference to 3. So I'm all set. Now I'm going to go and see 3D EMPro view to see all connectivities are okay. Okay. Oh, so thick film resistor is parallel with metal 6. Now I don't want to disturb the ground plane. Okay, anyways, we are practicing. So how about I move thick film resistor to the top, right? So instead of doing any other edit, I'll go to the substrate. There's no way I can remove the ground underneath. So anyway, so I'll have to, okay, I'll go to substrate and move this thick film metal to adjacent to the same layer as the metal 7. So I'm going to delete this from here on map, and then I'm going to add it along with metal 7. And this one I'm going to name, I'm going to choose this to be a 100 ohm per square material and 9 micron expand or to the top or above, and I'm all set. This is along with 7 and says save and close. Now I go to EM setup and look at 3D EM preview. 3D EM preview. Okay, so now this looks correct. So this is connected now. So we have a Wilkinson divider with 100 ohm in between. Okay, so let's set up the remaining settings. So this looks okay. According to me, it is connected. Right. Okay, so now I am going to set frequency from 9 to 11 gigahertz as adaptive. Then I'm going to go to options. Okay, output all frequencies, right? Save the currents for all frequencies. Options, mesh, edge mesh, transmission line mesh, and then create a EM model and hit simulate. So we are all set. Let me check the ports once more, whether they are having right reference. So they go from the ground up to the signal, so they look right? So they are referenced right, so that's fine. So we are ready for the simulations and hit simulate. So let's see what happens. If everything is right, the answer is going to be 50 ohm on all the 3 ports, correct? Okay, so it is doing the meshing at 11 gigahertz, mesh refinement, reducing the mesh size. Okay, so I guess it's done. Meshing is done at 11 gigahertz. Now it is doing the simulation. Okay, so I guess it's done. Okay, so now I'm going to look at S11, S22, S33. First of all, to make sure everything looks okay, S11, S22, and S33. Okay, so well, they are close to 50 ohm, right? So return loss better than 15 is possible. And let's look at S21 in dB and S31. So this is 3.4, right? So S31 in dB. Okay, that's also right, close by. So now I want to put S11, S22, S33 on the same graph. Okay, this S11 is off because of that 50 ohm line maybe. So later we will shorten this one. Okay, so S2233 are close to 50 while S11 is slightly off. This may have to do with the lengths also. You can slightly adjust the length also. Okay, so I'm going to put everything on the right hand side axis, S11, S22 and S33. S22, S33. I'll put on the right hand side axis. So they are better than 15, right? So the worst is S11, but it's still better than 15. So I think I'm done with the two-way Wilkinson divider, right? Okay, maybe. Okay, this I'll change to green so that it is visible. So S2233 look good, but S11 is slightly off. So I'm going to do one more simulation where I'm going to shrink the 50 ohm line if that is the reason. So first of all, I'll go to simulate and clear mesh, clear momentum mesh. Then I'm going to move these ports to the side like this. Move the ports to the side, delete this, and then I'm going to move 100 micron in. So edit, move relative 100. Okay, I can move 50 more in or maybe 100 more in. No, connector won't fit there, so let it be 100 only. And yeah, let's put the ports back. Okay, let's go ahead to EM simulation setup and hit simulate again. Say OK, and it is going to simulate. So this is the two-way Wilkinson divider. It's going to be slightly improved. Maybe it is the length of the lines itself. You can refine this, but it's going to take time. So I'm not going to do that. This is the last time I'm doing. So it is going to do the mesh at 11. It's going to do mesh at 11. And it comes out to be almost the same, right? Let's see. Okay. Okay. So it's doing that. It's meshed it. Let's keep an eye on S11. Okay, slightly moved, not much. So maybe the lengths of these two branches have to be reduced a little or increased a little so as to improve S11. But it's good enough. It's better than 15 point something. So we are done with this. Let's look at the phase also. Okay, first of all, let's go and see how the currents flow. So if I go to post-processing visualization and I put the power in port 1. Okay, so at 10 gigahertz roughly. I'm going to put the power in port 1 and hit animate. Port 1, yeah, say hit animate and change the scale for here for the legend to 1. Okay, so now I can see that the power is dividing into 2 and flowing in 2 arms. What I want to make sure is that they are in the same phase. So I'm going to go and plot the phase of S21. So go to phase S21 and then I'm going to do minus phase S31. Should be 0. Minus, so minus phase S31 is 0. Okay, so just click OK. Okay, and yes, the phase is almost 0, phase difference between the two ports. So the power is coming out in the same phase. It's just divided into half. So there is an insertion loss of around 0.4 dB on each branch, right? Okay, so here I guess I'm gonna stop. Thanks a lot. Thank you very much. We'll see the next session. We'll do some more passives. Yeah, thank you. I'm gonna stop here. 1 hour 16 minutes.